In an upcoming video, I am going to put a custom power factor adjustment panel on the generator on my truck. So in order to understand the depth of my genius, you will need to first understand what power factor is and how it works. Now, do not be intimidated. Power factor is easier than you think, I promise, and it doesn't require any math to understand. All you really need is just the concept, no math required. There are three types of loads, three types of things that you would power. The first, the ideal load is just basically a resistor, just some form of current shunt. That's it. Just shorted across your power supply, in this case just regular 120. A second very common type of load is an inductive load. Technically, almost everything is an inductive load, almost everything is an inductor. As far as you're concerned, if it doesn't have a coil of wire around some form of substantial iron or ferrite or something like that, it's not an inductor. As far as you're concerned, it has to have a massive inductance, a massive magnetic storage capacity in order for it to really matter. If it's a small inductance, you don't care. So this motor would have to be much larger for you to actually be concerned about its power factor. The third and final form of load is much less obvious, a capacitive load, and we will come back to this and you will understand this. Power factor, very simply, is the relationship between current and voltage. So, for example, this is a perfect resistive load. You just put some sort of shunt across your 120, and as the voltage rises, the current rises. They rise together, boom, perfectly in line. The peak voltage corresponds to the peak current. The highest point on this current curve is exactly in line with the highest point on this voltage curve. Easy. This has a power factor of 1. Power factor ranges from 0 to 1, 1 being perfect, like this, and 0 would be 180 out of phase, so the current would be exactly opposite the voltage. You will never encounter a power factor of 0. Basically, you want the power factor to be as close to 1 as possible, so the further away from 1 it is, the worse it is. That's really all you care about. The first variant in power factor is the inductive load, and this is the most common problem you will run into with power factor. This is why you care about power factor right here, because a massive inductor will have a lag between the voltage and the current. Why is the current delayed relative to the voltage? Simply, an inductor resists changes to current, to states of current, whereas a capacitor resists change to states in voltage. So what happens is, when you first turn on your inductive load, you get what's called an inductive spike. The voltage begins rising, but your inductive load, your inductor, has 0 amperage flowing through it effectively, and so it fights this voltage. So what happens is, the voltage is pushing on this inductor and it's forcing current through the inductor, and the inductor doesn't want it. So once the voltage reaches its peak, the voltage is pushing as hard as it can into the inductor, trying to force current, and the inductor is delayed in responding to that. By the time the inductor reaches peak current, the voltage has already begun to decrease. Now, beyond this point, more current is flowing than should be flowing because the inductor now has stored this current and it's reached its peak, and now it wants to maintain this peak. So as the voltage falls, the inductor is kind of like a spring unwinding, pushing out, and it forces more current to flow than the corresponding voltage should allow. And so it's kind of like, well, I thought you wanted more current, and it just keeps forcing current. And then, of course, the voltage hits 0, and as it continues going down, you can see here, when this voltage is at 0, if you follow this line up, the current is way above 0. So as the voltage continues dropping below 0, the voltage is now negative, but the current is still positive. It's only as this voltage is approaching its peak that you can see here on this particular graph, the current is approaching 0. And so then as the voltage peaks and begins decreasing again back towards the positive direction, the current only then begins to come down in the negative direction and peak. And so basically it's a fight back and forth. Voltage pushes this way, the inductor fights it, then voltage pushes this way and the inductor fights it the other way, and it's a constant fight back and forth. Why do you care? Why does this matter if these two sinusoidal waves are out of phase? The reason you care is because as the voltage fights this current, it actually draws effectively more current. This wastes power. So as this power is fighting this inductor, and as there's this delay in here, I don't know if it necessarily consumes more current. I don't know if it necessarily increases the amplitude of this current wave. It might, but it effectively consumes more power. And actually, when we hook up my truck, we will find out how the power factor affects the current, because I believe it does. I believe it actually increases the current. But either way, whether it increases the amplitude of this wave or not, the effect is, with this out of phase, this puts an increased demand on your power supply, whether you're getting your power from a power company or, in my case, a generator on my truck. So this is why it's important. So should you care about your power factor? It completely depends on who you are, where you are, what your situation is. So, for example, if you're running a huge factory that has, lots of motors and things, and you have a giant power bill, your power consumption is massive. Improving your power factor could significantly improve your electric bill, and it would save you a huge amount of money. And in a lot of cases, if you run an industrial facility, there will be an extra charge for having a bad power factor. The power company will actually keep track of this power factor, and you'll get a massive fee if it's bad enough. That's not always the case, I don't believe, but in some instances it is. So because you're using so much power, even a little bit of savings, that calculates out to be a lot of money. So it's worthwhile to correct your power factor. Now, if you're somebody, just in your house plugging stuff into your wall, you generally don't care about power factor for two reasons. First of all, you're not using so much electricity that changing your power factor would really have any effect on your bill. The extra amount of money you're paying on your bill, if you have a bad power factor, is so little, it's almost negligible. It's really not worth your time and effort to correct your power factor for your home use. And the second reason a general Joe Blow in his garage doesn't care is because, generally speaking, consumer appliances come with their power factor corrected as is. So if you buy something with a large motor in it, a lot of times it'll come with some sort of capacitor on that motor, if the motor is big enough, if the inductor has a large enough inductance to warrant it. So basically, your appliances are going to be close enough anyway. That's how they're going to come from the manufacturer. Now, if you're like me and you have a generator, then power factor actually becomes very important, because the better my power factor is, the more stuff I can do with my generator at once. If I have a really bad power factor on something, then I very quickly run out of available power on my generator. I won't be able to run as much stuff, if you will. So I want to build a panel on my truck so I can manually correct power factor, so that way I can optimize the amount of power that I'm using on my generator, and I can run the most number of things possible. Now, I have a 7.5 kilowatt generator, so I have a huge capacity. Do I need to optimize my load? No, probably not. My generator probably puts out more current than I will ever need to worry about. However, just because I like more, I would like to have the ability to correct power factor. Should I ever be in a situation where I'm like, oh shoot, I'm running out of watts that my generator can deliver, I need to optimize this power factor so I can get the last little bit of wattage out of this generator and run as many things as possible, should I ever be in that situation. So how do you fix this? Well, that's where we come into the third type of load, the capacitive load. What happens is, when you're at 0 volts, and you start off from the beginning, this capacitor is fully discharged. So as the voltage increases from 0, this capacitor is drawing a huge amount of current, and it takes a lot of current to charge this capacitor up, even to these lower voltages. Before this voltage gets to its peak, the current going to the capacitor is beginning to taper and beginning to drop off. The capacitor is approaching the fully charged state, and so it no longer requires this massive amount of current. So the current begins to decrease. Now the voltage is still increasing, and it still increases the voltage in the capacitor. So current is still flowing, but it begins to slowly taper off as the capacitor becomes full, and it gets closer and closer to the voltage that is being supplied to it. And then as your voltage begins to drop, your capacitor will discharge and it will try to maintain this voltage. Capacitors resist changes in voltage, and so current will begin to flow in the other direction to try and supply this voltage. And so what happens is the net effect is your current wave is moved before the voltage wave, whereas with the inductor it was moved after. You can see here, this is the symbol for power factor, and it gets complicated with the cosine of whomever while you calculate the distance between these two graphs. You find how far apart, how far out of phase these two are. You don't necessarily need to know that math. All you need to know is this symbol means power factor, and then one means the power factor is ideal, and then less than 1 in either direction indicates a slightly poorer power factor. That's all you really need to know. So this is our graph here with our inductive load. So this is a problem. This is what we want to fix. So how do we fix it? It's very simple. All we have to do is combine these two graphs. The inductive load, which has the current is slightly delayed, and then the capacitive load, which has the current slightly before. Well, before, after, well, they average out to the same. We can average these two graphs to the perfect ideal power factor, the ideal current consumption. And this is what we want if, like in my case, we have a generator and we're trying to optimize what we can get out of it. Practically speaking, you have an inductive load. How do you fix it? Well, you simply find a capacitor, an AC capacitor, of course, that has a capacitance equally as massive as the inductance of your inductive load. Now again, no math required here. A bigger inductive load means you need a bigger capacitor. You really don't need to mess with actually calculating this out. You can just do it with trial and error, and that's what I'm going to do on my truck. Is I'm going to have some sort of switching mechanism, and we will come back to this when I have my final design, and I'll let you know what works and what doesn't. But I'd like to have some sort of knob, and the knob will increase the capacitance across my 120, and as the capacitance increases, it will move this current sine wave further and further and further to the left, and that will cancel out this inductive load, which has the current move to the right. So it'll move this here, and I'll just keep cranking up the knob until these two are about in line. Now, how will I know when these are in line or if these are out of line? Well, I'll simply have a digital meter on my truck. It'll tell me the voltage, the amperage, and the power factor. It'll just be just a number. It'll have this symbol that I showed you, and then it'll have a number between 0 and 1. So if the number is 0.95, say, I probably will not bother fiddling with the power factor. But if I get a number on that power factor meter that is exceptionally low, maybe like 0.7, 0.6, something like that, I will adjust my knob, and I'll simply turn the knob up, and the number will increase. And I'll just keep turning up the knob until I get to about 0.99, and then I'll leave it. The power factor will be ever so slightly behind phase, but it's close enough that my effective power usage is correct. I'm not drawing excessive power. So I don't actually need to know the capacitance. I don't need to know the inductance. I don't need to do any math. You just turn the knob up until the little display says the number 1 or the number 0.99. So that's all I really need. So I have two potential designs for my knob here. I was thinking about either simply having some sort of potentiometer or resistor in series with this capacitor across my 120. And so a capacitor is basically a battery with 0 internal resistance. That's why a capacitor explodes when you short it out, whereas a battery will make something glow red hot. The battery makes something glow red hot, and it doesn't instantly discharge its power because it has an internal resistance. Inside of itself, it stops all of the power from going out instantly because it's a chemical reaction. So as the chemical reaction progresses, it delivers current, and then that current decreases as you run out of reactants and you approach the products. Whereas a capacitor, you short it out, nothing glows red hot, it's just an explosion, boom, instantly. All of the power in this gets discharged. Well, when you put a potentiometer in series with this capacitor, I think, we'll find out, I think that will limit the current going into this capacitor, that will limit the current as this capacitor discharges. So I believe, and I could be wrong, I believe that limiting that current will effectively limit the capacitance. Now, if I have a really big capacitor and I hook it up across 120, because the capacitor has zero internal resistance, it will charge instantly and discharge instantly, and so it will have a very large lag on this graph. But I think by increasing the resistance, because 120 is 60 cycles per second, there's only so much time that this capacitor is charging. Once that time runs out, it's about 1/20th of a second, the power reverses, and now positive becomes negative and vice versa. The polarity switches. And so the capacitor begins discharging and then charging in the opposite direction. So I think by increasing the resistance, I will effectively bottleneck this capacitor, and I will limit the capacity that it is able to charge up to before the voltage changes directions or begins to taper off. So, and we'll find out, and I'll look into this some more. My other option would be to have a rotary toggle switch, and basically you have 0 and then you chunk and you hook it up to a small capacitor, chunk, a medium, chunk, larger. And so basically the potentiometer would be infinitely variable, it would be completely linear, whereas the toggle switch, it would just be set values. So, you know, maybe the power factor would increase by, 0.01 each time. So if say for example, my power factor was reading as 0.85, chung, 0.86, chung, 0.87, chung, 0.88, and I just keep until I have enough capacitors hooked up in parallel that I'm able to match my inductance and I get close to 1. Just a quick note, it is possible that my potentiometer in series with the capacitor won't work because the capacitor will not reach capacitance. It will limit the current flowing to the capacitor. Part of the reason I think this current peaks here is just because the capacitor is approaching fully charged. And if you had a resistor in series, it would limit the current going to the capacitor, but the capacitor would not be fully charged. So it would take the maximum current allowed by that resistor for a longer period of time. So yeah, that might not work. That might make my graph totally weird, and it might not function as a power factor correction. I don't know. I'm gonna have to see. I love learning and building new things, and I hope you do too. So click that subscribe button and keep on learning with me, and I'll see you next time.
Yeah, man. There it is. So this is super crazy dangerous. That right there is Balin Mania, and we are going to do something really stupid today. It was a terrible idea. Balin might die. It was making me uncomfortable. Go, Balin!
You riding this?
What the fuck is happening?
Balin said not to talk crap about this camera. It's a piece of shit.
This is so unbelievably sketchy. Why would you put me through this, you jerk?
That's the power of really old engineering.
It'd be nice if it didn't kill me. It's not required.
I felt it fucking pop.
Make a wish, everyone. Make a wish. Not okay. You went too far. This guy, man. This guy.